You ever wonder how analytics dashboards can just crunch millions of data points, like in milliseconds? Well, the secret is often a super clever data structure called a segment tree. And look, if you're prepping for coding interviews, this is one you absolutely positively need to know. So let's break it down.
So, picture this. You've built an analytics dashboard. A user wants to know the total sales between, say, day 100 and day 200. Simple enough, right? But what if you have millions of data points, and more are streaming in every single second? How do you give them an answer instantly, without the whole system just grinding to a halt?
So the obvious answer, right? Just loop through days 100 to 200 and add up the sales. And look, for a small data set, that's totally fine. But when you're dealing with massive scales and thousands of queries per second, that simple loop becomes a huge bottleneck. And O of n, or linear time complexity, is just way too slow for the job.
Okay, so if a simple loop is out, what's the alternative? We need to pre-process our data in a much smarter way. And this is where the pure elegance of a tree-based solution comes into play. Let's actually build one from the ground up.
Okay, so here's the textbook definition. It sounds academic. What does that actually mean in plain English? Well, the key idea here is that a segment tree isn't just holding the raw numbers. No, it pre-calculates and stores information about different chunks of the data, things like sums, minimums, or maximums. And that pre-processing, that's the secret to its speed.
To make this super concrete, let's work with a simple little array, 1, 3, 5, 7, 9, 11. We're going to use this example for the rest of this explainer. Just imagine each number is in its own little box, all lined up. So now we're going to build a tree structure right on top of this array. The very bottom level, the leaves of our tree, they're going to match up one-to-one with our numbers. So we'll have a leaf node for 1, another for 3, one for 5, and so on, all the way to 11.
Okay, now here's the magic. This is the core idea. As we move up from the leaves, each parent node stores the combined value of its two children. So a node above 1 and 3, well, that's going to store their sum, which is 4. A node above 5 and 7 would store 12. You see? We keep doing this all the way up to the single root node at the top, which holds the grand total for the entire array, in this case, 36.
All right, so we built the structure. That's cool, but what's the payoff? How does this thing actually help us answer our range queries so ridiculously fast?
So let's ask our tree a real question. What's the sum from index 1 to index 3? Looking at our array, that's 3 plus 5 plus 7. Now, we know the answer is 15. But how does the tree get there so fast?
And here is where the magic happens. See, the tree is smart. It doesn't bother going all the way down to the leaves for 5 and 7. Why? Because it sees it already has a pre-calculated node that represents the sum for indices 2 and 3, which is 12. So it just grabs that pre-computed node along with the individual node for index 1.
And by combining just those two values, 3 and 12, it gets the final answer, 15. Did you catch that? We answered the query by touching only 2 nodes instead of 3 separate array elements. That is the efficiency gain right there.
So why is this so blazing fast? It all comes down to the tree's height. For a balanced binary tree, the height is logarithmic compared to the number of elements. This means, even if our array grows to 1,000,000 items, a query only has to travel a tiny pass down the tree to get the answer. And that is how we get that incredible O of log n time complexity. It's a total game changer.
Okay, so fast queries are awesome, but what if the data itself needs to change? And not just one element at a time, but entire ranges. This is where we need to give our segment tree a superpower, a really clever technique called lazy propagation.
And this happens all the time, right? Let's say you want to add a $3 bonus to every single product in a certain range. Well, going through and updating each element one by one puts us right back at our slow O of n loop problem. We need a way to update ranges just as fast as we query them.
The solution is this brilliant idea called lazy propagation. And I love the name because it's exactly what it sounds like. We're going to be lazy about doing the work. Instead of immediately updating every single node that's affected by the change, we just leave a little sticky note on a high-level parent node that covers the entire range. So how do these sticky notes actually work? Well, first, we tag a parent node with the pending update, say +3. But we don't do the work yet. We're being lazy, remember? It's only later, when a query actually needs to access one of those children, that we push down the update. We apply the change to the children, and then we clear the note from the parent. We only do the work when it's absolutely necessary.
And because we're so clever and lazy about this, it means updating an entire range is just as fast as a query. We only have to place a few sticky notes at the right levels of the tree. This lets us keep that amazing O of log n speed for pretty much everything, both range queries and range updates.
All right, so you get the theory, but how do you actually apply this in a technical interview and show that you've truly mastered it? Let's get into your interview playbook.
Okay, first things first. You have to know your complexities, non-negotiable. Building the tree takes O of n time, because you have to touch every element once to get started. But after that initial setup, the magic happens. Point updates, range queries, and even those lazy range updates are all O of log n. Space-wise, it's linear, O of n, since the tree size is just proportional to your input array. This table is your cheat sheet. Know it inside and out. You know, a classic interview question is to compare a segment tree to its cousin, the Fenwick tree. Here's the deal. The segment tree is like a Swiss Army knife. It's super flexible. It works with any associative operation, like min, max, or sum. The Fenwick tree is more like a specialized scalpel. It's simpler, faster, and uses less memory, but it's really only optimized for sum-based problems.
And finally, let's talk about the traps, the common mistakes that trip people up. Make sure your operation is actually associative. That is a non-negotiable requirement. Don't forget the identity element, like 0 for sums or infinity for minimums. And be extra careful with your array indices and the logic for pushing those lazy updates down the tree. Trust me, this is where 90% of the bugs happen.
Okay, theory is great and all, but to really truly get this, you got to get your hands dirty and actually write the code. Look, if you forget everything else, remember this one thing. The entire power of the segment tree hinges on this simple mathematical property, associativity. Because combining the parts gives you the exact same result as combining the whole, we can pre-calculate these segments and recombine them on the fly to get our answers. That's the whole game.
So what's your next step? Your mission, should you choose to accept it, is LeetCode Problem 307. It is the classic segment tree problem with point updates and range sum queries. It's the perfect problem to lock in everything we just talked about. Give it a shot and good luck.